Okay, proper close.
Yes, they should be proper and closed in A, not in the whole space but closed in A. So we are basically using this definition to show that the closure of irreducible subset is irreducible. I I am only able to solve one, and the partial part of 3. The problem number two seems trivial, is using some kind of Jones lemma type argument, but I am unable to do that. So I will discuss the solution in the next class or whenever I have the solutions. So I will do the 21 and the second part of 3. Let y closure equal to C1 union C2, where C1 C2 are proper closed set in y closure. Since y closure is closed in X, C1 C2 are also closed in X. Thus we can write y as y equal to y intersection y bar y intersection C1 union C2 since y is irreducible. C1 intersection C2 equal to y, or C2 intersection y equal to y. Note that both of them are closed. C1 intersection y, C2 intersection y are closed in y. Now C1 intersection y equal to y implies C1 is in y, C1 closure in y closure. Yes. And C2 intersection y equal to y implies C2 is contained in y, C2 closure is in y closure. Okay. Yes. Inequality should be the other way around. C1 intersection y equal to y means y is subset of C1. Y closure is subset of C1 closure. Y is subset of C2. Y closure is subset of C1. This implies y closure equal to C1 closure, or y closure equal to C2 closure. Therefore, and from these two we can conclude that, let's see start, therefore by star y closure is irreducible. Yes, please look at the proof, and if you have any comment, please. Anyone tried this problem? Anyone tried this problem? Five-star inverse Excel. Excel is element of here. We are taking three images. So all such Q belongs to Y such that Y-star Q is in Excel. Phi inverse Q is in Excel. If not in phi inverse Q. Phi f not in Q. This is by definition y of phi f. Therefore phi is continuous. A is an ideal of A. Five-star inverse VA. Such that just a minute. files adjective register and subset. Okay. Files adjective. Then phi is a homeomorphism. Okay. Okay. Note that. For in adjective homeomorphism. The extension conversion property for all t1 speaking. Therefore, phi star y equal to this is phi inverse q this is clearly prime ideal, then immediate it was a prime ideal. Okay, so oh, yes, you need that. Is a prime ideal. The extension is also prime ideal. Any prime take P, and if P is a prime ideal containing car phi, we want to show that P is in there. P extension is in B, and by our observation P extension completion equal to P, which contains control. Therefore we will take Q to be P extension. This implies phi is phi star is surjective. Why I am writing? Phi star is car phi. No problem. Define psi from V car phi to Y. Take any prime ideal and map it to the P extension. Now we need to check that. Okay. Now we need to check the now. Phi compose psi applied at P. Phi star is psi P. Phi star is P extension. P extension contraction. It is P. Psi compose phi star. Phi star is psi compose phi star of Q is Q contraction extension. Contraction extension, which is same as Q. Just a minute. Is it true? Yes. Therefore they are inverses of each other. We need to therefore they are inverses of each other. The only thing remains to show that psi is continuous. So we need to show that psi is continuous. Let continuity of psi. Continuity of psi. Let V belongs to V car phi lambda is in V car phi V any net such that P lambda converges to P. We need to show that phi P lambda converges to phi. That is the continuity. This establishes the continuity of phi. Okay. Let yg be any basic open set around P extension. That is, G is not in P extension. That is, F equal to phi inverse G is not in P extension contraction. Yes, which is P. Therefore, P is in XF. So we get an open set around P. For this open set, there is some lambda 0 is in lambda such that P lambda is in XF for all lambda greater than lambda 0. Okay, that is F not in P lambda for all lambda greater equal to lambda 0. That is G not in P lambda extension for all lambda greater equal to lambda 0. That is P lambda extension is in YG for all lambda greater equal to lambda 0. This is exactly psi P lambda equal to belongs to YG for all lambda greater equal to lambda 0. This shows that psi is continuous. This completes this proof. For any which is phi, which is psi, then phi compose psi inverse equal to psi inverse phi inverse. 7. And the 7 is saying that A is integral domain with just one prime ideal, non-zero prime ideal, and K be the field of fraction. And B is A mod P times K. Okay. Given space K is 0 and P. And what is B's? And B A mod P times K. Given and in a map phi a to a mod p times k sending any x to x bar comma x. So problem is to show that phi is not an homeomorphism. Okay, so spec a mod p cross k is this set. This is times k and a mod p times 0. Note that phi star of a mod p times 0 equal to what is that? Phi, yes, spec is this, okay, yes. So phi star a mod p equals 0 maps to 0 and phi star 0 plus p cross k maps to p. Phi star is continuous, but the inverse of phi star is so phi star is 1 to and on to and also continuous. But phi star inverse is not continuous. Because phi star is not a closed map. Problem number 22. Problem number 22 is saying for this problem we need to discuss something else. Ideals of product ring. Okay, one thing, how the ideals of product ring look like? Any guesses? we claim that every ideal of I equals j are of this form for some ideals okay, let or say A be an ideal, then pi 1 under the map pi 1a pi 2a are ideals of R and S respectively, and the question is why. Claim A equal to pi 1a cross pi 2a. Let x comma y belong to A, then pi 1 of x comma y equal to x belongs to pi 1a, pi 2 of x comma y equal to y. Okay, x comma y goes to x comma y goes to y. Standard projection maps. Y is in pi 2a. Therefore x comma y is in pi 1 cos pi 2a. This intuition is clear. On the other side, the other one, let what to say, pi 1a pi 2b is in A comma B belongs to A. We want to show that this is indeed in the ring, in that ideal. Okay, we have to show that pi 1 is in A, pi 2 is in A. Okay, A is in ideal A. So therefore pi 1 is in A, pi 1 A equal to pi 1. Well, it is an ideal. X comma y over x plus 0. in A. Yes. Pi 1 is in the ring R, pi 2 is in the ring S, pi 1 A has a element R. How to show that? It is as follows. A is in that ideal implies 1, 0 is in that ideal. This implies A, 0 is in the ideal. Similarly, B, 0 is in the ideal, means 0, 1 into B is in the ideal. These two together implies A, B is in the ideal. Now look at the ring morphism. Where it is. Yes. Now pi 1 R, let's call it R cross is 2R, it is pi 1, it is R cross S goes to S, and any S goes to S by 0, it is I1. Similarly, pi 2 any S cross Y goes to Y, any Y goes to 0, y. So I1 compose pi 1 of some element. Yes. So if we have any element A, if we have any element A in the ring, first is go by pi 1A, then is by pi 1A, and B goes to 0, B, then pi 2B, and then it goes to 0, B. So by 2 this ring morphism, just a minute, by these two ring morphism it follows that pi 1 of pi 1 of A and pi 2 of B, these two elements, this element is in what is my ideal, pi 1A plus pi 2B, I have taken an element is in the ideal A. So this implies pi 1A was pi 2B, pi 2A. This set is contained in this set, and this set is contained in pi 1A cross pi 2A. So these two together implies this ideal looks like pi 1A times pi 2A. So we have seen that any ideals of the product ring looks like product of any two ideals from that corresponding ring. This will help us to classify the prime ideals of a product ring, which are as follows. And for general case, use induction. Show that spec A is a disjoint union of open subspace xi, where xi's are canonically homomorphic to spec A. Yes. So I am going for the two case. Let P belong to spec R process. Then P equals to some ideals A times some ideals B. P equal to some ideals I cross J, where I is an ideal of R, J is an ideal of J. Since E belongs to spec R mod S, R mod S quotient P is integral domain. This implies R mod S by I is integral domain. This implies R mod I times S mod J is integral domain. Is integral domain. Now a product ring cannot be an integral domain if neither of them is 0. Is one of them is not 0 and another is not integral domain. Therefore I mod I equal to 0 ring or S mod I equal to 0 ring. Therefore no. Therefore case 1, R mod I is integral domain. S mod J is 0 ring. Otherwise it cannot be an integral domain. And case 2 is R mod I is 0 ring. S mod J is an integral domain. By case 1, I is in spec R, J equal to S. By 2, J is in by 2, I equal to R, J is in spec S. So what we, oh my god. Okay, so 75. By 1 this, by 2 this. Therefore, what we see that P equal to I cross J equal to is either P cross S, P is in spec R, or R cross Q, Q is in spec S. They are conversely any ideal of the above form the prime ideal of R cross S. Therefore, spec R cross S is hard to say. Spec R cross S union R cross spec S. So this is the part we want to discuss. Now 22. Now we are solving the problem number 22. For the general case, use induction. The proof is similar. We find pi j product ai equals to 1 to n to aj, the jth projection now. x1 is to xn goes to xj. Note that pi a is surjective by the problem. Okay, by the problem this 21.4 by the problem 21.4 spec B is homeomorphic to V of kernel phi. By 21.4 spec aj is homeomorphic to V of kernel pi j, but kernel pi j is this product ai I equal to 1 to n no, not like this. A1 cos aj minus 1 0 at that position aj plus 1 cos an. This is kernel pi j. So V of kernel pi j is this such that P belongs to spec aj. Then this is what you need to prove, that you show that spec A is disjoint union of open and closed subspace xi where xi are canonically homeomorphic to spec ai. Yes. So okay, these are called spec A. 76 spec aj which is homeomorphic to V of kernel pi j, these are xj, by our previous observation we see that by our previous observation means this one is a disjoint union indeed. We see that x equal to union xj, j equal to 1 to n, and x xi intersection Sj equal to 5 for all I not equal to j. This proves the first part of the problem. This one, converse part. Conversely, what is the converse part? Pk is disconnected when either of 0 ring. Conversely, this neither of these 0 ring is this contains an idempotent. So if A is isomorphic to A1 times A2, AIs are not 0 ring, then take the element 0, 1 or 1, 0. They are the non-zero, non-trivial idempotent element. What is 3? A contains an idempotent element. We want to show that the spec A is disconnected. Suppose E not equal to 0, 1, E belongs to A is idempotent. Then A is isomorphic to A mod 0, isomorphic to A into E into. Since E is idempotent, is square equal to minus E. A by 1 minus E by Chinese-Similar theorem. Note that neither A or 1 minus A is the whole thing. Therefore, spec A is disconnected by the first part of the theorem of this problem. Okay, so 1 implies 2. That 1 implies 2 is if spec A is disconnected, then it is direct product of two rings. If spec A is not, so if it is not direct product of two rings, then it is not disconnected. I will leave that. I will do it later. The additional part is the spectrum of a local link is always connected. That follows from the question exercise 2. Next part, follows from exercise 12. For each if the set xf is both open and closed in X. We know xf is open, and what about xf is closed? Okay, xf is closed. xf is closed means f is open. Okay. To show xf is closed, let p lambda is in xf be in it such that p lambda converges to p in X. We want to show that p lambda is in X. If not, then f is in p lambda. F equal to f square is in p lambda. This means f square minus f, or that is 0, is in p lambda. This implies f into 1 minus f is in p lambda. And I want to show that is in p. I am writing p lambda, p lambda. Is in p, is in p. Since p is prime, f belongs to p, or 1 minus f belongs to p, and both of them cannot be in p at the same time, right? Now we know f is in p. Since f is in p, this implies 1 minus f is in p. If both of them is in p, then their addition is in p. That means 1 is in p, which is a contradiction. So 1 minus f is in p. F is not in p. That means p is in X of 1 minus f, this set. So for this open set, there exists lambda 0 greater than lambda such that p lambda is in X of 1 minus f for all lambda greater than lambda 0. Now what we have assumed, for lambda equal to lambda, for lambda equal to lambda 0, p lambda is in xf. Yes, p lambda is in xf. P lambda is in xf minus 1. So 1 minus f. This is f into 1 minus f. This is f square minus f. This is 0. The 0 element. This is empty. Contradiction. Therefore, contradiction to what? Contradiction to what? This one. We have assumed that p is not in xf. Contradiction to that, p is not in xf. We have shown that p is in xf. That implies xf is closed. This proves the first part. 2. Problem 2 saying xf union xf. Okay, we will do for 2. N equal to 2. XF union XG should it? Okay. XF union XG is VF intersection VG, VF intersection VG whole complement. Yes. So it is V of F comma G whole complement. It is same as V of F comma the ideal generated by this complement. This is F plus G minus Fg whole complement. This is X of F plus G minus Fg. Then we are done. This is the set X of condition which is both open and closed. Okay. Let y be any subset of X which is both open and closed. Since y is open, y equal to union xf sum f. Now y closed implies y is compact as x is compact. This implies y equal to union xf I 1 to n. Since xf's are open cover of y, now y equal to x g for some g. By problem B D. X is a compact house of space. We know X is compact. We need to show that X is housed off. Suppose X is not a housed off space, then you can find P and Q, two different ideals, prime ideals, and a net which converges to both P and Q. I think I have not done this problem. I am unable to show that X is housed off. No, I am not unable to show that X is housed off. Also, this problem will do later part. Okay, I have not done this problem. I am unable to solve it. So we will do it later. Hopefully in the next class. The last problem. The last and final problem. Next minute. 71. maximal ideals are of this form. Okay, so M is a maximal ideal. I need to show that M is of this form. Okay. I guess Atiya proved that. Atiya have proved that in that take any maximal ideal and consider the common zero set. All such x such that if x equal to 0 for all n, if V is empty, if V is we want to show that V is non-empty. If V is empty, for each x there exists f x is in M such that f x is equal to 0. Now if it is continuous, there is an open neighborhood so that f x does not vanish by compactness, finite number of neighbors cover them, blah blah blah. So V is non-empty. Now V is non-empty, so there is a point x is in V. Then M is in M x, and since both of them are maximal, so we are done. We are done by part 1. Now part 2. We need to show that mu is injective. We need to prove that mu is injective. Part 2. Since x is compact Hausdorff, x is normal, that is any two disjoint closed sets in X can be separated by disjoint open set. Okay, so given x comma y belongs to x, x not equal to y, there is f belongs to cx, f comma g such that f of x equal to 0, f y equal to 1 and g of x equal to 1, g of y equal to 0. So this implies that the set mx is not same as my. This shows that mu is injective. The third part, what is the part C? We need to show that the map mu is a homeomorphism, that is mu is continuous, mu inverse is continuous, and all the blah blah blah. Okay, so part C, mu is a homeomorphism. Let x lambda be okay, mu is a homeomorphism. Let x lambda be not like that. Let x is in x and x lambda be in it such that x lambda converges to x. We want to show that mu of x lambda converges to mu x. Let u tilde f be an open set around mx. That implies if not in mx, that implies fx not equal to 0. So there exists ux, an open set where f of y not equal to 0, y is in ux. For this ux, again there is lambda 0 belongs to lambda such that x lambda is in ux for all lambda greater equal to lambda 0. This implies f of x lambda not equal to 0 for all lambda greater equal to lambda 0. This implies if not in if x lambda not in this implies if is in this implies what m of x lambda is in u tilde of f. This proves the continuity of mu. This implies mu is continuous. Now I want to show that the mu inverse is also continuous. Note that mu is bijective. To show mu inverse, continuity of mu inverse, we show that mu is a closed map. But mu is a closed map. Let mx and my two different maximal ideas. That implies x not equal to y, since x is Hausdorff, there exists uf, ug inside x such that x is in uf, y is in ug, and uf intersection ug equal to mt. We claim uf tilde intersection ug tilde, this is also empty. This is also empty. If there is some element is in just check it. I will not explain. This implies that what that this implies, and mx is in uf tilde m. This implies max cx is Hausdorff. This shows that state if closed set X is compact implies F is compact. Mu F is compact since mu is continuous. This implies mu F is closed since target space is Hausdorff. Is closed. This proves that mu is a homeomorphism, and we are done. Yes, we have solved almost all the problems. I have left few of them since I am unable to solve them by my own, so I need to revisit all these problems. I will solve them, and then in the next class maybe I will give all the solutions. This will conclude this chapter.